pick almost any software engineer or software developer and ask him, what is the time complexity lower bound for a search algorithm? The answer, which has become today almost a reflex, is O of n log n time complexity, which is also called linearithmic time complexity. However, if you search Wikipedia for the running time of a Radix Sort, it's saying, hold on to your chair, O of n. How could that be, you ask? Well, it makes a few assumptions on the keys and we look deeper inside the keys. So the trick to get an O of n time complexity, yes, O of n time complexity for a search algorithm is to pick inside the keys, and if we have some preconditions on these keys, then we can achieve this, and this is what we'll see here. So while it's true that the lower bound of search algorithms, which are based on comparisons, is O of n log n for non-comparison based, specifically for algorithms that do their tricks like Radix Sort, it is actually O of n. Let's say we generate some random numbers and we have the range 0 to 1000, and we generate numbers, and lo and behold, they are already sorted. In this case, what would be our time complexity for sorting this algorithm? It would be O of 1, because the array is already sorted. So you can just return this array to me and it would be already sorted. So with different assumptions, we can get different time complexity for sorting. If our assumption is that the array is already sorted, then the time complexity would be O of 1. If our assumption is going to be that the keys are structured such as integers, and actually inside the computer everything is an integer, yes, even a game is like just a series of numbers and computations, so everything is numbers. It all comes down to zeros and ones. We have electricity or we don't have electricity. So we can utilize this Radix Sort algorithms in many cases. We can transform what we have into numbers, and then we can use the Radix Sort to sort items in O of n. Example of sorting algorithms which are not based on non-comparisons, such as examples of sorting algorithms which are based on comparison-based method, which is comparing the items, is a quick sort, merge sort, heap sort, bubble sort, for example. And all these sorting algorithms, because they are doing the comparisons between the items, are like saying, okay, I have an abstract method which receives two items, item A and item B, and this abstract method compare would know how to do the comparison. And once you have this, you have a comparison-based algorithms, and you are using this method. And all these comparison-based algorithms would have a lower bound of the time complexity of O of n log n. Here is a naive intuition behind how we can do sorting without comparing anything, because frankly I have to tell you that doing a sort without comparing the items, it seems like magic. How can we sort items without comparing them? Right? Because if I have a few numbers and I want to sort them, and I say this one is bigger than this one is smaller than this one, and I'm sorting. But no, in Radix Sort we don't do this. We don't do any comparisons. Okay. So the way to think about it and the way to get the intuition into how to sort items without a comparison is that, let's say we have a list of items. We have generated a random list of items, and the range of these numbers, we are generating a list of numbers with a range. Let's say that the lower bound of the range is 0 and the upper bound of the range is 1000. And They are unordered. We just got a list of numbers unordered from the range 0 to 1000. How could we sort them without comparisons? One way to do this would be to create a new array. We just need to create a new array with range. So if we said that the range of the numbers that we have generated is from 0 to 1000, then we can create an array of 1001 items from A of 0, array item 0, and up to array item 1000, and then we scan all the items in the original list, and wherever we are facing an item, then we mark this place in the array. So let's say we have the items 101, 202, 50, and 900. So we start scanning the input array. The first number is 101. We go to the array, to the place 101 to this index, and we mark it with 1. No comparisons. We go to the next item, 202. We now go to the array, to the index, to the new array, to the index 202, and we mark it with 1. We scan the next item in the input array. It is 50. We now go to the new array, and in the index 50, we mark 1. The last item is 900. So we go to the new array, to the helper array that we created, to place 900, and we mark it with 1. If we had another 900, we would mark it with 2. So you see, we just scan the items in the input array one by one, which is a linear time. And then we use the helper array to mark all the items that we had. Then all that is left is to scan this helper array. Whenever we face that the index has the value 1, then we take the index and print it. Okay, if the index had the value of 2, then we would print its index twice. This was a linear time, but we have here a limitation because we needed our helper array to actually have the size of the range of the input numbers. So while this is okay if we generate 1000 numbers from 0 to 1000, we know that the range, like the minimal item is 0 and the maximal possible item is 1000. We can scan the input array and find the minimal item and the maximal number, and then we could know what is the range of the temporal array that we are creating. This is great, but if you have like a gigantic range, then you would need to have a helper array which is very, very big. And this is where this sort fails, because it wouldn't be simply an O of n, where n is the number of items in the input array. It would be proportional to the range of the input array. So even if you had like only a few numbers, but the range would be 1 million, you would need 1 million items in the helper array. So this is not good enough. But now we are going to improve it and get to the Radix Sort. The Radix Sort is saying this: I'm going to look at the numbers and look at a single digit. Like you put all the numbers one below another, not horizontally, but one below vertically, one below another. And then you start from the rightmost digit, which is the least significant digit. What you're doing now is take the number and put it inside an array, but the array now, the helper array, is only going to have the range of the radix, which means if it's a decimal counting system that we use, then we have an array from A of 0 to A of 9, 10 items, because we have 10 digits. Then we look at the first number. What is the least significant digit in the first number? It was 1. So we go to the index 1 and we mark it with the number. We put the actual number there. Okay? There are a few better ways to do this, but now we put the actual numbers. And then we continue scanning the array. We continue scanning the array from the least significant digit to the most significant digit, and whenever we see what is the digit that we are seeing, and we take this number and put it inside the index. Let's take an example. Let's say that we have the numbers 202, 153, and 103. Okay, we look at the first number. We have three numbers, 202, 153, and 103. We look at the first number, it is 202. What is the least significant digit? It is 2. So we go to index 2 in the helper array and put the number 202. Great. We continue with the least significant digit and we move on to the next number. It is 153. What is the least significant digit? It is 3. So we go to index number 3 and place the number 153 there. We move on to the next number. It is 103. What is the least significant digit? It is 3. We go to the index number 3. We already have there the number 153 because it also ended with 3, and we put the number 103 next to it, just after it. Next, we move on to the middle digit, but now we don't scan the original numbers as we got them from the input. Now we scan the numbers according to the order in the helper array, because we want to preserve the order that we got from the least significant digit. If we go again to the input array and start scanning it, then we would lose all the information that we got from sorting by the least significant digit. And note also that we do not do any comparisons. So let's repeat again what we did. We had three numbers, 202, 153, and 103. We went to the least significant digit. It was on the first number, it was 2. So we just place it on the index number 2. And then we had on the second number, we had 153. The least significant digit is 3. We place it at index number 3 and so forth. And now we move on to the second digit, but we do not scan the original array. We scan the array that we already began to sort by the least significant digit. And now the middle digit of the first number 202 is 0. So we go to index number 0 and we put there 202. Okay, it's like a new helper array. We start all from the beginning, but as we scan the previous helper array, we get like the ordering by the last digit. And now we do reorder by the second digit. The second number that we have in the original list that we see is 153. What is the middle digit? It is 50. So we put it on index number 5. It is alone there. There is no other digit. We go to the third number, which is 103. What is the middle digit? It is 0. So we put it on index number 0 and we already had there 202. So now in index number 0, we have first 202 and then 103. So they are unordered, but we would fix this because now we repeat the cycle again for the first digit. We have three digits. We went from the least one, the least significant one, to the most significant one. And now we have reached the hundredths, the most significant digit. So we look at the first number that we see in the helper array from the previous stage. The first digit is 2. So we go to index number 2 and we put the number 202. We look at the first digit of the next item from the helper array from the previous stage. We see that it's 1, so we place it on index number 1 and so forth. And in this way, you have seen that we can sort an array without comparing and only by scanning all the items multiple times. There are a few more clever ways to do this, but we won't do this in this session. I think it was hard enough to transform this and pass it in a podcast. And we have seen, to sum up, that so far we have just used the operations of comparing two keys and exchanging two records whenever we wanted to do a sort, but actually we can do this without a comparison. And when we do this without the comparison, then we used only part of the keys. When we did the comparison-based algorithms like merge sort and bubble sort, we compared the whole key. We used it as a single unit, right? But in Radix Sort, we decompose the keys into a sequence of fixed type pieces. And in our case, the radix, this is why it's called the Radix Sort, is 10, because we have 10 digits from 0 to 9. And the radix sorting algorithm are also based on the abstract operation of let's extract a digit from the number and then assign it into an array. Once we do this, we are able to take immediately the number and put it inside an array. So we were heavily dependent on the fact that we have numbers, but as we said, in computers, everything is actually a number. It's possible to do the radix sort from the most significant digit to the least significant digit, and in our example, we used the way to do this from the least significant digit to the most significant digit. And as most computers also have some bitwise and shift operations, that then they can do this efficiently. They can actually scan the numbers very efficiently, although if you do the shift, you would need to do multiple shifts in order to find the right digit that you want to actually use. And you can look at it as moving the numbers inside the middle array. We say we move the numbers, we place them on the correct place according to the least significant digit, and then we move on up to the most significant digit. And in this way, we were able to actually have a sort that runs in O of n. I think this was very interesting, and I will see you in the next session.